Hello and welcome to the Springfield AWS user group. Today we're going to be talking about Let's Encrypt and secure certificates. My name is Jason Klein. I have 15 years experience deploying and managing many paid and free certificates. I'm going to talk about the background behind secure certificates and why they're the foundation for trust and security on the web. We'll dive into a few different scenarios where we'll issue certificates from different vendors and what that looks like, including Amazon and Let's Encrypt. And then we'll talk more about how Let's Encrypt works before we dig into the different certificate types. Not only the differences between the vendors, but also the certificates themselves and the validation types that are out there. Once we get through that, we'll show some examples of generating and inspecting your private keys and your certificate requests so that you know what that looks like. And my goal is for you to be more familiar with the actual certificate material and know what you're seeing so that if you're dealing with certificates, it's not such a mystery. And then we'll cover some best practices and tips and tricks that I've learned along the way, address common issues and pitfalls, and end up the presentation with some resources that you can rely on in your certificate journey. So why use secure certificates, commonly known as SSL certificates or TLS certificates? Number one, they encrypt data between your users' browsers and your servers. So they provide the security that prevents people in between your end user and your server from viewing that data. Initially, secure certificates were used primarily for financial websites, I think online banking, or any websites that required a username and password, but they've expanded far beyond that. There was a time when you could watch the traffic on a network and you could see someone logging into a site like Facebook. And even though you couldn't see their username and password because the username and password was encrypted, you could see every single time that they made a website request, and every single one of those in the clear request would include their current cookies. And if you were to take those cookies out of their payload and put them into your own browser, Facebook thought that you were that person. So it's become very important for people to be able to rely on the security of different websites and not fall victim to man-in-the-middle attacks. Also, trust is a huge reason why we use secure certificates. More and more browsers are warning users not to trust in secure websites, but it goes beyond that. We hear about a lot of online phishing attacks and malware attacks, and with phishing attacks, we would see where websites would be essentially copied, and you would receive an email, click a link, go to a site. It will look just like the original site. And from an end user point of view, they had to know to look at the domain name and make sure that they match. That's still true. But with the advent of HTTPS everywhere, it's become more and more difficult for those type of scammers to fool you, because now they also have to deploy HTTPS, and normally alarms are going to go off if something doesn't look right. Either the user is going to be more likely to catch that discrepancy, or the web browser is going to alert them. But in the end, the goal is for end users to be able to trust the content that they're seeing and know that it's coming from you. A couple more reasons that secure certificates are becoming more and more prevalent. Search engine optimization, or SEO. Google and others have confirmed that HTTPS is a ranking factor in their algorithms. So if you are not using HTTPS in your website or web application at this point, you're going to take a ranking hit in search engines. And then more and more sites are deploying HTTP2, which allows all of your web assets to be downloaded through a single connection. Whereas, let's say you design a website in the past that would have your main web page and then a logo and some images and some style sheets and some JavaScript files. Every single one of those assets would require a connection to the server to request and download the asset. With HTTP2, all of those can be downloaded through a single binary stream, but HTTP2 requires HTTPS. So you definitely need to have secure certificates if you're going to implement HTTP2. Now, how are certificates used to encrypt data? We're going to step back here a little bit and go through a little bit of theory just so that you have an idea of how all of this comes together. There's more to it than this, but this should give you a pretty good idea. The gist of it is when a user connects to your secure website, the user's browser requests a secure session. Now, we're going to cover deploying secure certificates a little bit later, but let's assume your server is already set up with a secure certificate. Your server will respond with the certificate, and the user's browser will validate the secure certificate. We'll talk a little bit more about that in the next slide. But at that point, the user's browser responds with a session key that is encrypted with the server's public key. And secure certificates are based on public-private key cryptography. The gist of it is the server can have a private key and a public key that it shares with anyone. And the user can use the information in the public key to encrypt data that only the server can decrypt with the private key. So at this point, the user has responded with a session key that is encrypted with the server's public key, meaning anybody watching that communication cannot read this session key. And then the web server decrypts the session key and establishes a secure connection with the user. At this point, the data going back and forth between the user and the server is encrypted with that session key. It's not encrypted with the public-private key. That's fairly inefficient, whereas this constant session key or symmetrical encryption is much more efficient. So I mentioned we would talk about how the certificates are validated by the web browser. As someone who installs and helps maintain SSL and TLS certificates, this is very helpful to understand because most of the issues we run into can be troubleshooted and resolved just by understanding this process. So your browser, whichever browser you choose, think about the browser built into your OS, whether that be Edge or Safari or a third-party browser that you install like Firefox from Mozilla or Google Chrome. All of those browsers are going to ship with trusted root certificates, or they're going to rely on the trusted root certificates built into your operating system. But nonetheless, that trust starts somewhere. And when the user's browser requests a secure website, the server replies with the secure certificate, like we'd already talked about, and optional intermediate certificates, also known as the certificate chain. When the browser verifies the secure certificate, it starts by making sure that the subject in the certificate, or what we know of as the website host name or fully qualified domain name, match what you're trying to access on the web. And if that matches, then the browser attempts to verify the secure certificate is signed by a trusted root certificate authority. And I included a diagram that shows what that might look like in terms of the different browser certificate paths, but let's take a look at certificate number 1. Generally, when you get a secure certificate, it is not signed directly by the root certificate authority or root CA, which would be up here in green. Instead, the certificate is going to be signed by an intermediate certificate authority. There are a couple different reasons for that, but first and foremost is security. That root certificate authority, the certificate material is kept under tight lock and key. They do not want that to get out in the wild or be compromised in any way. So generally, it's under tight control, and that certificate is going to sign these intermediate certificates that either belong to the vendor that maintains the root certificate authority or your third parties like Let's Encrypt. And then that intermediate certificate is allowed certificate authority features that let it sign its own certificates, like certificate number 1 or certificate number 2. And so when your web browser is browsing to a secure website with, say, certificate number 1, then the website should reply with certificate number 1 and the intermediate certificate, assuming that the web browser is aware of the root certificate authority. And at that point, the web browser can confirm the chain of trust because it's able to confirm certificate 1 is indeed signed by intermediate certificate number 1, and intermediate CA is indeed signed by this root certificate authority, which I trust. Let's say it's Firefox. I maybe have the root certificate authority built into my list of trusted certificates, or maybe it's something like Edge or Safari, where the root certificate authority is built into the Windows Trust Store or the Mac keychain. So at that point, you've verified the chain of trust. And we'll talk a little bit more about how to deal with some of these issues, but a very common issue is that people forget to or don't understand that they need to include the certificate chain when they configure their certificate on their web server. And so what you'll sometimes see is that the web server will send certificate 1, it will not send intermediate certificate number 1, and even though there is a trust chain from the root certificate authority to intermediate certificate 1 to certificate 1, the web browser can't make that connection because it's missing a piece. Now, you might get into a situation where some web browsers work and others do not, because for whatever reason, some web browsers happen to be aware of this intermediate certificate. But you can't count on that. You have to include the intermediate certificates when you're configuring your certificates on your web server. It's probably the biggest takeaway today when we're talking about troubleshooting. It's the number one problem I see people run into. So with that being said, once the browser has verified the secure certificate, the browser will check for revoked certificates. These used to be called certificate revocation lists. Early on in the SSL days, the idea was that anytime a certificate was revoked, let's say the private key was accidentally compromised or published online and could no longer be trusted, or it was lost and a new one needed to be issued. When you would go to get a new certificate, you could essentially revoke the old certificate and it would no longer be valid. That way, if someone else had a copy of it, they couldn't pretend to be your website, because browsers wouldn't trust it. But the way certificate revocation lists, or CRLs, worked was that all of those certificates were listed in a long list, and it became longer and longer and longer to the point where it was slowing down web requests. I mean, browsers were expected to check these huge lists and download these lists, and it just wasn't feasible at some point to continue to do that. So OCSP was born. And the gist of it is that browsers can now send a request to a website, and the website will confirm whether or not that certificate is revoked. And we'll talk a little bit more about that in a moment. But let's dive into issuing different types of certificates. I'm going to talk about a traditional domain validated certificate first. So if you've never worked with certificates, or your experience is limited to a single vendor, like maybe certificates through a hosting provider such as Amazon where they're completely managed, or certificates through an automated vendor like Let's Encrypt, you may not be familiar with what this workflow looks like. But traditionally, domain validated certificates would start with you as the customer generating a private key and a certificate request for a specific website fully qualified domain name, or FQDN. Now, that may be a single name like app.example.com, or it may be a combination of names like example.com and www.example.com, also sometimes known as the bare domain and the web domain. The idea there being, if you're issuing a certificate for a website, people may attempt to browse to the website through the bare domain, like example.com, or through the web domain, www.example.com. And in either case, you want them to be able to connect over a secure connection. So you generate that private key in SCSR, and then you go to your vendor. Sometimes that means logging into a web portal. Sometimes that means using an API, but you begin a secure certificate order. You send them your certificate request or your CSR material, and then you select the domain validation method. And that may be them sending you an email, them validating over HTTP, or them validating over DNS, and then you paying the fee. But those validation methods with a domain validated certificate allow the certificate authority to verify that you have some sort of administrative access to the domain. So With an email validation, if you were to choose that, they would likely perform a whois lookup on your domain name, and then they would offer up that administrative contact or owner contact or technical contact email to you. However, in common day, pretty much anyone who registers a domain name is going to use a privacy service which hides those email addresses. So if you're choosing the email validation level, just know that you'll most likely have the option of some generic names, hostmaster at your domain or admin at your domain. We typically use hostmaster at the domain. Whenever we're managing domains, it's just habit for us to forward that hostmaster address to our central management address, so that when those type of requests or validation emails come through, we're able to get to them. If you're validating through HTTP or DNS, you'd typically have to either upload a specifically named file to a specific location, and sometimes even with specific file contents or payload, or you'd have to create a specific DNS record with a specific payload, or a DNS record that points to a specific host name. I've seen both. But the goal being that it's going to be some sort of random web file or DNS record that wouldn't have already existed. So the assumption is if it exists when they check it, you have access to manage the website or the DNS for the domain. So after you've started your order, you would wait for the validation email to come through, or you would go ahead and manually create that HTTP file or DNS record, and then the vendor would perform the domain validation. So that may be seeing that you've clicked on a link in the email or checking for that file or that DNS record. And ultimately, once the vendor has been able to perform the domain validation, they issue you the certificate. They might email that certificate to you. They might notify you that it's available for download. They might respond through an API, but one way or another, they'll get the public certificate material to you, and that certificate is signed by them. So there's nothing in the certificate material that they send you that needs to be kept private, because that certificate is going to be sent to every single person who connects to your website. But the thing that makes it special is the fact that they've signed it. Now, let's talk about issuing certificates through a couple different vendors. We'll start with Amazon. Since we're an AWS user group, I like to try to tie these topics into AWS. So I'm going to go through a couple slides that show what the Amazon Certificate Manager console looks like when you're requesting a cert. If you were to go to the AWS console and then to Certificate Manager and request certificate, you would land on this Add Domain Names page. You could add one or more names, and in this particular example, we added 2 domains. But going back to the prior slide, you could certainly add example.com, your bare domain, and then www.example.com, your web domain, and proceed through the process. Now, before I continue, I do want to mention, contrary to the prior slide for traditional domain validation, when you request a certificate from Amazon, you do not have to pay a fee. Sometimes people assume that there will be a fee for this, just like there is for every single other thing that they could possibly provide, but no penny here or dime there. They include this as a service to their customers. Now, the catch being, when you request a certificate through Amazon, it's only usable by Amazon services. So their goal here, I believe, is to make their other services as easy to use as possible. So we start by specifying the names that we want, and then we specify the validation method that we would like to use. Like the prior slides, you have the option of DNS or email validation. You don't have the option of HTTP validation with Amazon. But one thing that I love is that the DNS validation, if we were to choose that and click next, it integrates very well with their DNS service, Route 53. So this particular example domain certificate that I'm showing here on the slides is using a domain that is hosted in Route 53. So on the first screen, you'll see that the 2 names are pending validation, and each name has to be validated separately, even if they're from the same domain name. But if you expand that first name, you'll see that there's a big blue button, Create Record in Route 53, where rather than having to copy and paste that information into your DNS provider, you press the button, you expand to the next name, press the button again, click continue, and then you wait for validation. And when everything is within the Amazon ecosystem, validation takes seconds. I believe I refreshed the page 20 or 30 seconds later, and the status went from pending validation on each of these names to issued, and validation showed success on both of these names. So it really is that easy with Amazon Certificate Manager. At this point, the certificate is ready to be used in AWS services, and I listed a page on this slide that talks about the different services that can use Amazon certificates, but we primarily use these certificates with Amazon CloudFront or with the ALB application load balancer, and they work great for both. And if you were to go into either one of those to configure the certificate, it would be available immediately. The other nice thing about this is that you can deploy and manage these certificates through CloudFormation templates if your domain is in Route 53, since everything can be automated and there's no manual user intervention when it comes to validating the domain. Okay, we talked about traditional certificates and Amazon certificates, and now let's talk about Let's Encrypt certificates. There are really two common methods of requesting a Let's Encrypt certificate. The most common, I would guess, would be through a hosting control panel. If you're hosting your web app through something like DigitalOcean or Netlify, my guess is that they have checkbox configuration where you say, yes, I want this, and they take care of everything for you. You may not even know if they're issuing the certificate through Let's Encrypt because the process is so transparent to you that it's out of sight, out of mind. But that's probably the most common use case these days. The next most common use case would be using the CertBot Acme client. This is an open source client published by EFF that is available on many different platforms. Our experiences with Debian Linux, but pretty much any flavor of Linux and other OSs have this software. So if you're standing up some sort of Linux server, this would be the way to go. I showed our common use case, 2 steps. If you were to stand up a Linux server that needed a secure certificate, you would run the CertBot client once to request the free certificate for the website. You'd specify the FQDN, in this case the -d app.example.com. If you needed multiple host names, you just keep adding -d parameters. So this command could potentially have -d app1.example.com, -d app2.example.com, -d app3.example.com, and so forth. And CertBot would be able to generate a secure certificate that protects all 3 of those host names. The catch being, the host name needs to be pointed at that local web server. So if you are generating a secure certificate with Let's Encrypt, before you were to run this first command, you would want to point the DNS for that host name to the server. Because when you run the CertBot cert-only command, it's going to basically tell Let's Encrypt, I would like a certificate for this host name, and Let's Encrypt would reply and say, okay, I'm going to validate through HTTP. You need to put this file out in your web folder, which we specified as the web root in this command, and the CertBot client would do that and tell Let's Encrypt that it's ready for validation. Let's Encrypt would connect to the server in real time, look at that file, make sure it does exist, and then issue the certificate. And we'll get a little bit more into what that flow looks like, but that's the gist of it. And then you would need to specify an email address so that Let's Encrypt can contact you if there are ever any issues related to your certificate. We get emails every once in a while if they notice some sort of configuration issue on our end, or if we're needing to reissue certificates. Let's say there's a security issue on their end. It's very rare, but we've used Let's Encrypt so much that we have seen some of those. So you do want to provide a valid email address, just so that you can be aware when they notice something on your end that may need attention. So that's step 1. Step 2 is scheduling CertBot renew to run every day or 2. Debian automatically configures CertBot to run a couple times a day when you install the CertBot package, but The reason that's important is, unlike traditional certificates, which have a lifespan of a year, these Let's Encrypt certificates only have a lifespan of 90 days. They are meant to be automatically maintained, automatically renewed. That's just one of the fundamental principles behind the Let's Encrypt infrastructure. So you need to be sure that you have a job scheduled to run certbot renew on a regular basis. And when it runs, it only renews the certificates that are set to expire. So if you end up with a server with one certificate and you just installed it yesterday and you run certbot renew today, nothing's going to happen. It'll check the certificate, it'll see that it expires in 89 days, and it will be done. But if you run that again in 2 months, it's going to see that the certificate expires in less than 30 days, and it will go ahead and renew it early. It's not going to wait until day 89 or day 90. At least from our experience, certbot seems to always renew certificates right around the 60-day mark. And so we set up our monitoring to alert us if certificates expire in less than 4 weeks or 28 days. And very rarely do we get an alarm, but every once in a while something will go wrong and a server won't be automatically renewing certificates, or we'll have some outbound firewall rules that are blocking outbound requests to certbot, or a server may need to go through a web proxy to get to the internet, and certbot's not configured to use the proxy, so it can't communicate with the outside. And so we catch different problems like that through our monitoring, but they're always self-induced. We've never really run into any problems with certbot renewals less than 28 days out that are the fault of the certbot client. You can learn more about the certbot client at certbot.eff.org. So this is more of a deep dive into how Let's Encrypt works. There's definitely more to it than this, but this should give you a better idea of what's happening behind the scenes. We've talked about the traditional process and then things like the Amazon process, which are fully managed. So those are sort of the two ends of the spectrum between manual issuing and completely managed issuing. And so this falls in between, in my opinion. And so it's good to understand what's happening since it is automated in case something goes wrong. The gist of it is that the certbot client sends a challenge request for a specific FQDN or specific set of host names, depending on whether you're requesting a single domain certificate or a multi-host name certificate. And the Let's Encrypt server replies with a list of available challenges for each of those host names, and also requests a verification signature. And that verification signature helps Let's Encrypt ensure that you do have control over the private keys that your certbot client claims to have when it's requesting to issue or renew these certificates. So the client sends the verification signature, and then the client performs the challenge. Typically, with the certbot client, that means the client is uploading specific file name and file contents to an HTTP website. Now, that can happen a couple different ways. In the prior slide, that example would write files to an existing web root. But the certbot client can also act as an HTTP server. So if you're generating a certificate for, let's say, a different service like SMTP or POP or IMAP, certbot can temporarily open up port 80, the HTTP port, listen for the challenge request from Let's Encrypt, and serve up the files that Let's Encrypt is expecting. And then after the client has performed the challenge, the server verifies the client signature and client challenge, and assuming all is well, Let's Encrypt issues the certificate to the client. That entire process takes only a few seconds. Compared to the manual process that can usually take minutes or hours or days, this is more in line with the Amazon Certificate Manager, where everything happens in a matter of seconds. And it's pretty amazing how quick it is. So now that we've talked about issuing traditional certs and managed certs through, say, Amazon and then certs through Let's Encrypt, I'd like to show you what it looks like if you were to generate private keys and certificate requests. So we're going back to issuing traditional certificates, just so you know what you're looking at. This information, it holds true regardless of the certificate type. All certificates have these fundamental sets of files. First, we'll start with RSA certificates. There are several different certificate types. I'm not going to get into those today, but I am going to demonstrate the two more common certificate types. Let's say you're issuing a traditional domain validated certificate and you need to upload a certificate request to your vendor. You would start off with one of these processes. You would generate a key locally. And so I took a screenshot of my terminal output after I ran a command, OpenSSL request, new key. And in this case, the current standard is to generate a 2048-bit RSA key. We'd write the key out to server.key, and we'd write the certificate request out to server.csr. And this is what I see as a user when I generate this, and this is very common. You'll see it generating the key. It'll ask for a passphrase. Typically, you would protect your certificates with passwords or passphrases, but in some cases I have seen where people will, after the fact, go out and take that server.key and they'll write it out to an unencrypted key. If you have an application or use case where the system will not accept the key, you can remove the password. Then we'll go in and we'll specify our country name and state name and locality name or city and organization name, and then we can end up with our common name, which is the host name. At this point, you'll end up with a server.key and server.csr that look a lot like the example here. This large block is an encrypted private key. This smaller block of text is the certificate request. In general, you can convert any type of certificate material to this format. This is often known as PEM, but it's text. It's not binary data. Pretty easy to work with and move around. It can be converted to binary files like PFX files, but generally when you're working with Linux services or Linux servers, whether that be Apache or Nginx or Postfix or pretty much any other server I can think of, all of them want this text type format. Let's look at generating an ECDSA key or elliptic curve key and its associated certificate request. These are becoming more and more common. I expect that Let's Encrypt will start issuing these by default in 2021. We're not seeing Let's Encrypt issue these quite yet, but that doesn't mean that it's not happening. I'm pretty confident that they've rolled out support for this internally in 2020. The difference being ECDSA uses elliptic curves instead of prime numbers like RSA has always done. With that being said, there is an additional step when you're generating these. Typically, you'll generate a parameter file, and then you'll generate your private key and your certificate request. And you'll see the first example command here shows OpenSSL generating a P key with a generate parameter option, and then you choose your algorithm, and then you choose your key options, and then you write those parameters out to a server.pem file. And these file names, by the way, can be anything, but you'll generally need to reference that output in the next command. So you could write that out to parameter.txt if you wanted to. And then in the next command, we request a new key, and we specify that this is going to be an elliptic curve key, and we specify that parameter file that we just created, and then we write the key out to server.key, and we write the request out to server.csr. And you'll see that it's generating a 256-bit elliptic curve key as opposed to a 2048-bit RSA key in the prior slide. The technology is different, so 256-bit doesn't mean that it's an eighth as secure as the RSA key. The security is measured differently, but it does ultimately mean that the key size is smaller, as you can see over on the right. But it asks the same questions as before, and then it generates those files. And if I show the contents of server.key, you can see that it's quite a bit smaller. I'm going to go back and forth, back to RSA, and then forward to the elliptic curve keys. And the certificate request is about the same size. And we're going to look inside each of those files next. Again, I do expect more and more people are going to go this route. When it comes to encryption, you're always going to want to look up what the current recommended standards are. Don't go off of these slides. But as it stands right now, we're generating RSA keys at 2048-bit or elliptic curve keys at 256-bit. But that can change because computers get faster and it's always a cat and mouse game. You want the keys to be strong enough that the fastest computers can't compromise them. And as computers get faster, that means you need stronger keys. So let's look inside these RSA request and private keys and see what's happening in here. If you want to inspect the certificate request, you could run an OpenSSL command. And by the way, all of these examples use the OpenSSL command line tool, which is generally available on most operating systems. If it's not already built in, you can download it. In this first example, we run OpenSSL and basically tell it that we want it to read in the certificate request and then not to output any files, but instead we want it to show text. And so that's this area, and I've added highlighting. The yellow highlighting, if it's too small to read, the first line basically shows a subject, and it shows the country is US, the state is Missouri, the locality is Springfield, the common name is www.example.org. And then I highlighted the public key algorithm, which is RSA, the public key length, which is 48-bit, and then further down the signature algorithm, which is SHA 256 with RSA encryption. These are the things that you would look at. If you were to inspect your private key, same type of command, only we're using an RSA command and then we're reading in the server.key. It starts by asking for the passphrase for the server key because you have to remember that's encrypted. And once you've typed that in or provided that, it can read the key and output this information. The server key is meant to be kept private. So like all of these files are just examples. I don't actually use them in production. They were just created for this demo. But you wouldn't normally publish this online, especially for anything that's in production. But going back to the certificate request, the output includes a modulus and this signature algorithm. And I highlighted the modulus in blue because this is common between the certificate request and the server key material. It shows the same modulus, but then it also shows your private exponent, your prime numbers, your exponents, and your coefficient, which the combination of those things are used to decrypt the information that has been encrypted with your public key. Whereas the modulus is something that is incorporated into the public key. So it's included with the certificate request because the certificate authority, when they generate your public key, they'll provide that in the key and they'll sign it. If we were to inspect the elliptic curve request and parameters and private key, you're going to see that it's quite a bit different. Rather than just having a common modulus, I've highlighted all of the fields that are common between the request and the private key. And you'll note that the only thing that isn't common is one private key that's 256-bit. The structure of these files is quite a bit different, but because of the way they're encoded, when I showed you the blocks of text, you don't really have to worry about this. You just see that it's a smaller block of text. The takeaways here, again, if you're inspecting the request, you're going to see the subject includes the host name, like www.example.org. You're going to see which public key algorithm is being used and the key strength. So in this case, it's an elliptic curve public key with a length of 256 bits. And then you're going to see the signature algorithm, which it's an ECDSA key with SHA 256. And typically those aren't something that you're going to have to look at, but if later on when we're going through the tips and tricks and troubleshooting, if you receive a warning about a signature algorithm or a key strength or something like that, you can use these commands to go back and look at your key material and figure out what went wrong. And then ultimately you may have to go back to the original commands where you generated the keys and generate a brand new key with a different key strength or with a different signature algorithm. If, say, it's been a few years since you've generated the key and now you're getting warnings because that key is just no longer sufficient. Now that we've pulled the curtains back and looked at what is inside that key material, we're going to move on to some more high-level stuff. We're going to compare Let's Encrypt certificates to commercial certificates. Number one, there are different types of certificates. Let's Encrypt only offers what I refer to as single domain, multi-domain, and wildcard certificates. Single domain might be app.example.com. Multi-domain might be the example we had earlier of your bare domain, example.com, and your web domain, www.example.com. But it could also literally be multiple domain names. So it could be app.example.com, app.example.org, app.example.net. If you were to have some sort of site that's responding to host names at different domains, all of those could be rolled into a single multi-domain cert. And then wildcard certificates, which would be, say, *example.com, meaning if your application generates host names on demand for clients, so a client logs in and creates a username, and then maybe their portal is username.vendor.com. Rather than your application having to go and request a new certificate every single time a new user enrolls, so jdo.example.org and then jsmith.example.org and so on and so forth, you can generate a wildcard certificate that covers all of those names up front and install that one wildcard certificate on your web servers or load balancers, and then they're equipped to immediately respond to any host names at that domain. If you are wanting a wildcard certificate from Let's Encrypt, you have to go through a few extra hoops because you do need to use their DNS verification instead of their HTTP verification to make sure that you have control of the DNS. They can't just assume because you're able to maintain files on one website that you can be issued a wildcard certificate for all of the sites at a domain. Other vendors provide all of these certificates, some for free, some for a cost, but several things that Let's Encrypt do not offer are certificates for IP addresses. So let's say if you're wanting to be able to allow people to browse to an IP address that your organization owns without having to go to a host name, or let's say they happen upon the IP address and try to browse to the web resource, you'd like for it to be able to respond over a secure channel. You can buy those certificates from other vendors, but that's sort of an edge case, so we aren't going to go into that a whole lot. Look at the links I provided if you want more information. And then other vendors also provide certificates for code signing. So if you publish apps to Windows or Mac or the App Store, nowadays more and more of the App Store environments are taking care of this for you, but there was a time when you would need to sign the app, and then if someone were to download it from your website, the Mac or Windows OS would trust it. And that's something you have to pay for separately. Let's Encrypt has made a statement that that's not really something that they're planning on doing. I included that link. If you're needing those type of certificates, you'd have to look elsewhere. Certificate term. I mentioned that Let's Encrypt certificates are valid for 90 days and automatically renewed after about 60 days. Compared to that, if you were to buy a commercial certificate, those are typically valid for a year. It used to be they were valid for 2 or 3 or 5 years, but over time, as the secure certificate landscape has changed more and more, the certificate vendors have agreed to only issue certificates for a year, or technically about 13 months. But the idea behind that is, with different secure certificate exploits that have happened over the years, they've found that people would install these long-term certificates on their web servers for 2 or 3 or 5 years, and then let's say a certificate is compromised and needs to be reissued. Those certificates just aren't getting the attention that they deserve until they expire. And so this has basically allowed the industry to force consumers to do a better job of keeping up on their certificates by touching them at least once a year. But I mean, the way we look at it at that point, unless you benefit from some of the other things that the commercial certificate providers can offer, every 1 year isn't much different than every 90 days. So it's great to be able to find a way to automate those renewals, and Let's Encrypt has been a great answer for us if we're needing to install certificates on Linux servers and not use a managed service like the Amazon Certificate Manager. I included a little bit more information in that link 5 about the change to 1-year terms. And then another difference between certificates, besides the type of certificate and the term, would be the validation levels. Today we've been talking about domain validated certificates, or DV certificates. Commercial certificates also offer OV, or organization validation, as well as EV, or extended validation certificates. We're going to dig into the difference between those in a few slides, but the gist of it is domain valid certificates are validated through some domain mechanism, whether it be email or HTTP or DNS, whereas the OV and EV certificates are more deeply validated, and they actually embed the organization information into the certificate. Another difference is the warranty. Some certificate vendors offer a dollar amount warranty with their certificate. A lot of people see that as a gimmick. It really depends on your situation. There is some merit to that offering. If you're in a large e-commerce business and you're dealing with a high dollar amount value, you may be interested in some of these larger warranties that basically pay out if the certificate vendor is at fault. Let's say you're using their certificate and there's some sort of technical problem that was caused by an issue on their end. Maybe they issued certificates that just weren't up to current standards, and then because of that, your site took some sort of loss, whether it be a security exploit or something else. You could file a claim with them and they could pay out to cover some amount of that loss. And on the flip side, Let's Encrypt, it's a free product. It does not offer a warranty. Amazon's in the same boat. I'm pretty confident that they don't include a warranty with their certificates. So that's a somewhat specialized difference. It's something to look into if you're operating an e-commerce site. I mean, you'd want to make sure that either your insurance or a combination of the two would cover losses due to a technical issue with the certificate. But that's definitely an edge case. Another one that's an edge case is the Trust Site Seal. It was very common for a while to have these little seals on secure websites that you could click on to basically receive proof, and I put that in quotes, that the website is trusted by a certain vendor. I included a link to a statement from Let's Encrypt essentially that said that they won't offer a site seal and they aren't convinced that that is a value add. So it's just not something that they plan to incorporate. But if you're looking at those things and trying to compare, in most cases, I would say that the warranty and the Trust Site Seal are probably not worth comparing. What you would want to look into if you're trying to decide between a commercial offering and some of these free options would be the different types of certificate validation levels. All of the free options are going to be domain validated. We've already talked a lot about that. Domain validation can be automated, can take as little as a few seconds. Organization validation, on the other hand, actually authenticates the organization. For example, the vendor may perform a DNB lookup or Duns & Bradstreet lookup and just make sure that your organization does exist, and then they would verify that the applicant has the right to request certificates for the organization. So maybe they're listed on the DNB lookup or they have a company email address. And once that certificate has been issued, which can take a couple days, and is installed on your website, it will be presented with the organization information in the certificate. If you go to some of the larger websites like Amazon and you click on the certificate inspector in your browser, you'll most likely see that it lists the organization name. That happens when an OV or EV certificate are issued. Also, some browsers will show different color bars for these higher levels of validation. With an OV certificate, you may see a blue bar. It seems that that has come and gone. I'm not seeing as much of that now, but the last browser that I believe I saw that in was Firefox, and I don't recall seeing that lately. Extended validation or EV certificates are the same as organization validation, except they do a deeper dive into your organization. That's something that they're most likely going to issue for your huge e-commerce sites. For a while, that would enable the green address bar on some browsers, like the blue address bar. I really haven't seen that much anymore. That validation can take 7 to 10 days. For larger sites and organizations, these validation methods would be a reason to look to commercial certificates instead of the automated certificates. And having an internal policy that certificates of this type only be issued allows those organizations to have better control over the certificates that are being used for their organization. Let's talk a little bit about certificate best practices. We're not going to deep dive into all of these because we're running out of time here, but when it comes to private keys and certificates,
You want to really dig into the key strength and making sure you understand and are using the correct key strength or an adequate key strength for the time. You want to be sure to protect your private keys. You don't want those to be published publicly. You don't want those to be committed with version control. Those need to be kept under lock and key. You want to be careful about choosing a certificate authority. It used to be that, free certificate authorities, stay away from them, they're a disaster. Let's Encrypt has proven that not to be true, but nonetheless, there are stories of certificate authorities trust being pulled from operating systems and web browsers. So if you're relying on a CA that all of a sudden has some scandal or compromise and browsers are pulling the plug, your certificates are no longer going to be trusted by those browsers when users try to visit your site. If you're using a CA other than a mainstream certificate authority, you might need to just keep up on the news and make sure that you're aware if they're having issues and you need to pivot to someone else. Be careful about which signature algorithms you use, and you ought to publish DNS CAA records, which are basically DNS records for your domain that authorize specific certificate authorities. I mean, in our case, we may list Amazon and Let's Encrypt, but the idea there is you don't want someone to be able to issue certificates from a compromised certificate authority, so you limit the surface area or which certificate authorities can be used with your domain. Configuration. There's a lot here to unfold. I'm not going to dive into all of it, but the idea is that when you're setting up your web server, you want to be sure that you're configuring proper certificate chains, protocols, ciphers, forward secrecy, key exchange, and you want to mitigate known problems. I'll give you some tips on how to address all of these here shortly. You want to be sure that you're managing performance. You don't want to implement excess security. I mean, there's a reason people don't generate RSA 16,000-bit keys. They'd be too slow. You want to implement session resumption and optimize your certificate settings and use HTTP2 when available. You want to implement content caching so that static files aren't requested over SSL over and over and over. You want to implement OCSP stapling. We talked about that as the successor to certificate revocation lists. Well, what if OCSP goes down? Then with OCSP stapling, your web server can make a request to those OCSP servers and serve up a request for up to 7 days, and the browsers will trust that request and be able to skip making their own OCSP request. HTTP and application security, you really want to encrypt everything. You want to secure your cookies. You want to be sure you're using secure compression, which often sadly means no compression, or at least no HTTPS compression. You want to look at your STS settings, your content security policy, and you want to avoid caching sensitive content. Now, like I said, a lot to unfold here. I listed a couple links that really dive into all of these, but the easiest thing to do to make sure you're keeping up with most of the best practices is test your secure certificate. If you're overwhelmed by these best practices or not sure where to begin, run an SSL server test on your application, and then resolve any of the major issues that prevent you from scoring an A. In the example I'm showing here, this SSL server test result was from a web application hosted on an Amazon application load balancer and protected by an Amazon certificate. I literally didn't have to do anything and I got an A. So that's the beauty of using a managed service like that. But if you're using Let's Encrypt with your own servers, you're probably going to have to spend some time on this and just fine-tune your settings so that you're not getting a subpar result, or heaven forbid a D or an F, meaning that you have some major issues and you're not really much better off than running without a certificate. We're wrapping up here. Let's talk about some common issues that you might run into. I don't recommend people use self-signed certificates. I mean, the exceptions are if you're developing locally or you have an internal corporate network, there might be a use case there. But if you are hosting a public website, you don't want to use a self-signed certificate because all of your visitors are going to receive security errors because they're not going to trust your certificate. Their browser just won't know who you are. We talked a little bit about shady certificate authorities. Be aware that certificate authorities can have issues. I listed 3 recent examples from the last few years, including 3 different certificate authorities that have been pulled out of browsers. Avoid using an incomplete certificate chain or no certificate chain at all. Don't just upload your public certificate. You need to include those intermediates that we talked about. Again, the SSL server test will check for these issues and will identify them if you have them. Make sure that you don't have a typo in your certificate request. Inspect your CSR and make sure that you spelled your domain names correctly. Otherwise, it just slows down the process. You don't want to leave your private key file exposed to others, so make sure the permissions on the file are adequate if it's on a public web server. And if you're storing it, don't just store it out in a group file share for all of the people at your company to see. You want to keep that under lock and key. And then track your renewal dates. There are services that can monitor your certificates and notify you if your certificates are coming up for renewal. I listed a couple examples of major services that have gone down because they weren't doing this or somehow missed a renewal. So you definitely need to track that if you're not using an automated solution. Let's Encrypt takes care of this for you, but it's not bulletproof like I mentioned. So if you're using Let's Encrypt, you still want to find a way to manage all of these certificates and monitor the renewal dates. If you're using something like Amazon, in our experience, they've handled all the renewals perfectly or notified us if there was a problem. As far as configuration tips, I already mentioned publishing CAA records. We talked briefly about OCSP stapling. This day and age, you should consider publishing an HSTS header on your website, which basically tells browsers not to connect to HTTP. This prevents downgrade attacks, cookie hijacking, other man-in-the-middle attacks. It's not necessarily recommended by the SSL test, so you will see that it is or is not enabled, but they aren't going to tell you you need to, but it's something to consider. And finally, don't opt out of certificate transparency log monitoring. Some providers offer the chance to opt out of that, but that has been implemented for a reason. Instead, benefit from it. Use a service that can monitor those CT logs and notify you of any certificates that are issued. That way you can catch any unauthorized certificates that are issued for your domains. If you're a large company, that might mean certificates that were issued out of protocol, maybe from the different vendor or maybe not through the proper channels. If you're a smaller company, that could mean catching someone trying to hijack your domain and use it to send spam, or some other malware. So either way, something to look at. And I listed CertSpotter as a possible service or self-hosted option for that. And finally, here's some resources. If you have additional questions, definitely look to some of these. Mozilla offers a SSL configuration generator for a number of different web servers. They also have their own website test. The third link is the website test screenshot I listed earlier. And then finally, you can test your browser. So there's an SSL browser test. If you have additional questions now or later, feel free to drop into the Springfield Dev Slack channel. Our channel is #AWS, or follow me on Twitter or GitHub. I'd love to hear from you. And thank you very much for joining today. Hopefully you took away a lot of great information about secure certificates and have a better handle on how to manage them or how to deal with any problems you might encounter. Thanks again.